I'm John Rosner, Program Chair, and we're very happy to have, as Michael said, three great speakers on the mystery of mass. An organizational point, we have to clear the hall as soon as possible after the session so that they can put the divider in, which takes some time. So if you're going to chat outside in the lobby. Our first speaker is Joe Incandela, who was an undergraduate and graduate at the University of Chicago, postdoc at Boston University, and a CERN fellow, and is now at the University of California in Santa Barbara. And he's going to talk about the discovery and the implications of the Higgs particle. Joe.
Okay. So I will talk about the discovery and the early characterization of a Higgs boson, at least, that we've recently discovered, as you know. Excuse me. I wanted to start by saying that I gave a talk, a slightly shorter version of this talk, to Fred Kavli once, and he was incredibly excited. And I share your comments about his enthusiasm. I was really surprised at how really excited he was about this discovery. So, as you know, this recently culminated in a Nobel Prize, but the story is quite long. And I'll try to give an overview of the basic physics, but mostly focus on the experimental effort and the discovery and some recent and even more recent results. So we have what we call the Standard Model. And this is something that over the last 100 years has been brought together as a result of the discovery of really many hundreds of subatomic particles and great advances of theoretical physics that involve some really tricky and really difficult realizations. And as a result, we have something that is like a new periodic table of the fundamental elements. We have 3 generations of quarks and leptons, which are basically the particles that you might say make up the structure of the universe. And then there are bosons, which are the forces and the force carriers. And this is one of the greatest achievements of 20th century science. As I said, there are fermions here. I like to show this picture because this formula is wrong. And I'm sure he did not make... So it tells you about dealing with the press. When they tell you to go to the blackboard and take a picture, make sure you watch what's at the back. And this is boson. And as I said, fermions are spin-half, typically spin-half particles, and bosons are integer spins in this case. And half-integer particles, of course, can build structure, Pauli exclusion principle. Integer particles like to be in the same state, and it makes quite a bit of sense that these are the particles that make up forces and coherent actions. And the entire Standard Model can be represented, actually, all of this work, as Carlo Rubbia once said, this 100 years and billions of dollars, and this is all we know. But that's a good thing. It's very simple, and it's all represented by one simple equation. And we feel very proud of our achievement. Here's another view of the Standard Model showing the masses on a log scale. There's a big difference between even just the electron masses and the top quark mass, which is the heaviest. We don't know what the neutrino masses are, and of course that's a big issue for the next decade or two. And these are open questions. Why are these masses so different? And there was one missing piece, which was the Higgs. And it wasn't guaranteed that it was there. It's a kind of bizarre particle. It has no spin, and no spin particles are rather problematic. And you'll perhaps hear more about that in the next talk. Okay, so why do we need the Higgs? Why did we introduce it in the first place? Well, most force carriers are massless, but we knew that the force carriers of the weak nuclear force, the W and Z, had to be heavy. And that was because the force is actually short range. And you know that you can associate with a mass a distance scale. So for a 200 MeV particle, you can associate a 1 Fermi distance scale. Now, if you just put the masses in by hand, things kind of work. But when you go to higher energies, the model breaks down. And in fact, you start getting probabilities greater than 1. And this is called unitarity violation. So you have an amplitude that it grows with energy squared. This is not good behavior. Now, the way out was to introduce the Brout-Engler Higgs mechanism, to introduce a scalar. And basically, the idea is you fill the universe with a field, and this field interacts with particles. It has to be a scalar field, and that gives masses to the particles, basically stops them from moving the speed of light, gives them longitudinal polarizations. But it introduces another diagram into the mix that has the same initial and final states, and therefore from quantum mechanics we know there's interference, and it actually gives you very nice regularization of the amplitude. The underlying theory can still be a gauge theory, even though we know that with gauge invariance, the gauge particles should be massless. And the reason is not that the laws of the universe are different, but the universe itself is different. The universe is filled with something. That was not what was originally believed. But the nature of the theory is somewhat hidden by the fact that the universe is permeated by this field, which has a constant vacuum expectation value. So here's my, well, it's not even mine, somebody's drawing of what happens. You have this field permeating the universe. It interacts with particles, basically shields their fields, concentrates their energy, creates massive particles. So that's my theoretical introduction. I'll move on now to the hunt for the Higgs at the LHC. This is a picture of the LHC, where the LHC is in the valley between the Jura Mountains, where the picture was taken, and the Alps, that's Mont Blanc. And you can see the sequence of circular accelerators that lead up to the big LHC. And I like this picture because it's a very pretty picture, but it also really shows the scale of this machine. The design goals were to really cover all Higgs mass values which were possible from basically 100 GeV up to about 1 TeV. The search there was also a big interest in searching for strongly produced new physics up into the multi-TeV region. And this is to actually solve some of the problems. This physics that I'm mentioning here is really related to the fact that if there is a Higgs, a scalar Higgs, then there's some other problems that have to be resolved, and new physics has to come in. Now, it took a long time. The first studies were in 1984, as you can see. It was approved 10 years later. Construction then started. Installation started in 2003. We had first collisions at low energy in 2009, and this took a lot of innovation, a lot of new concepts in magnets, cryogenics, electronics, computing, and it really took a huge worldwide effort by thousands of people. And these are very important points. It took patience, perseverance, and a lot of optimism to hang in there for so long in such a tough, challenging project. This is a picture inside the LHC tunnel. You're seeing here the dipole magnets. These are the most challenging part of the accelerator. There's 1,232 of them. They keep the beams on track in a 27-kilometer diameter ring, circumference ring. They run up to 8 Tesla. This allows 7 TeV per beam. As you know, that the momentum is limited by the strength, literally by the strength of the field and the radius of the machine. There's 7,600 kilometers of niobium titanium superconducting cable that runs at 12 kiloamps at full energy. And we operate at 1.9 degrees with 120 tons of superfluid helium. And it's like Swiss chocolate. I'll let you think about what I could possibly mean by that. Well, the magnets actually have a stored energy of 11 gigajoules, which is enough energy to melt 12 tons of copper. And it's actually the kinetic energy of an A380 at 700 kilometers per hour. The beams, how much do they have? They have 350 megajoules, which is the same as 23 kilograms of TNT or 15 kilograms of chocolate. So you probably didn't know that chocolate had more calories than TNT, but... So, in fact, with so much energy stored in the beam, there's great risk of damage if anything goes wrong. And we did have a serious incident, as you know. And after that, there's been tremendous effort made to make sure that we can run this machine safely. And right now, the machine is down for 2 years of work to even greatly improve its operation. Okay, I'll move on to the experiments. I'll start with ATLAS. ATLAS is a giant experiment. It has a weight of 7,000 tons, 3,000 kilometers of cables. It's 46 meters long, more than 6 stories high. I show some people here for reference. I think they're small people, but they're still people. I mean, and the size and mass is actually dictated by what's needed to measure the momentum of very high energy particles and to capture their energy. Given the magnetic fields that are used to actually cause the charged particles to travel in arcs from which we can measure their momentum. So there's about 100 million independent sensing elements. The same is true for CMS. Many of these things are very similar. Almost everything I say about one is true for the other, except for that we use different technologies. You can track up to 1,000 particles per event and obtain precisions of a few micron. And everything has to be fast, about 25 nanoseconds to 50 nanoseconds with 40 megahertz beam-beam collisions. And everything has to be very radiation resistant. We have up to 10 to the 17th neutrons per square centimeters on the innermost layers, which means a lot of radiation. Here's a very early drawing of what was planned for the ATLAS toroidal magnets for the outside muon detectors. This shows them being assembled in Hall 80 at CERN, and here they are installed. And again, I show you a person for reference. This is a giant detector. It's a very big collaboration, almost 40 countries, almost 200 institutions, thousands of PhDs, scientists, and something like 1,000 graduate students. And I just want to mention that the US is a very big part of ATLAS, with 44 institutions, about 20% of the authors, and a couple hundred graduate students. Now moving on to CMS. This is a picture of CMS. It's actually quite a bit smaller, but much heavier. It's twice as heavy as ATLAS, which means it's twice as heavy as the Eiffel Tower, in fact. But it's only 15 meters in diameter, and it's about almost half, just over half the length of ATLAS. And the reason for that is that we have a very, very strong magnetic field, which means we can make particles bend much more sharply in the magnetic field. Their trajectories can be arced, and we can basically track very high energy particles over a shorter lever arm. But the two detectors actually perform remarkably similarly. To first order, they're identical. To second order, one's better, a little bit more better at something than the other, but they're very, very similar in performance. CMS had to be built on the surface. It lowered in huge sections down 100 meters underground. That was no trivial thing because we only had 3 centimeters of clearance, bringing these million-pound objects down. This shows how it was done with a huge crane. And this was the heaviest piece with the giant solenoidal magnet, which is the most powerful magnet ever built. And as I said, it's about 4 Tesla. CMS is also a big collaboration of about 40 countries, 200 institutes, a couple thousand scientists, and about 800 graduate students, of which the US is, again, a very big part, about 30%. So how does it all work? Well, we collide beams, and the beams are made up of actually 1,380 bunches currently. They'll double that number in the future. And they are targeted to collide at about 4 places. And each time they collide inside of ATLAS and CMS, for example, you have about 20 or 30 pairs of protons that interact. Each bunch has about 150 billion protons, but protons are very small. And so you get an interaction rate of about 20 to 30 pairs. So here is a ZZ event as an example in CMS. You see from all of these other interactions, you see very highly curved tracks, which means soft energy, low energy particles. These are from the debris from other proton interactions. But one of the interactions produces something very spectacular, which are 4 very high energy, reasonably high energy muons, I should say. And when we reconstruct those, we find that there are 2 pairs of Z's. And when we reconstruct what the Z's come from, they would correspond to, hypothetically, a particle of mass of about 126 GeV. So as I said, there's 40 megahertz of beam-beam collisions. Very fast response required, about 25 nanoseconds. Particles are reconstructed with a precision of a few micrometers and 76 million channels of silicon detectors. And interesting collisions are very rare, so we only record about 500 events out of the 16 million collisions every second. But we still end up with a lot of data that we have to ship around the world. There were 22 petabytes collected in 2011 at CERN and 30 in 2012. These are shipped out along the computing grids that we have to about 250,000 processors worldwide in 35 countries. How well does it all perform? The accelerator, for its maiden voyage, so to speak, first run, performed incredibly well. There was, in terms of the fraction of operation time available for physics, in 2010 it was 16%, it went to 24% in 2011, 37% in 2012, which is really commendable for, as I said, for a new machine. We were setting new luminosity records. This is the luminosity in terms of 10 to the 33, hertz per nanobarn, which is 10 to the 33 per centimeter squared per second. And you can see that we were setting records frequently in 2010, 2011. Then things stabilized at about 7 times 10 to the 33 in 2012. The detectors also work spectacularly well. We had something like 3 continuous years of operation with the detectors at 95 to 100% functionality. And this allowed us to actually, both experiments in the end are basing their results on 90% of the beam crossings data. One big challenge, though, was the fact that we had so many interactions at the same time. Here's a real event in which each interaction has its own color, and you see the particles streaming out. Only one of these interactions will be interesting in any given triggered event, but you have debris from many others, and so you have to be able to deal with that. This shows, this is a nice little diagram from 2010. This shows what a typical, if you just pick events at random, they would look something like this. There'd be typically 2 interactions. In 2011, randomly picked events would look like this. And underlying physics, don't forget, is not changing. It's just the number of interactions that are overlapping that's changing. And in 2012, it looks like this. So we had, going into 2012, quite a challenge to be able to understand how to deal with this. This shows the distribution of the average number of interactions. In 2011, it was sort of 5 to 10. 2012, it was 10 to 20, or 20 to 30 toward the end. And to deal with this, which we call pileup, this pileup of interactions, we had to really rely on our tracking. The tracking detectors are magnificent in these experiments, and the granularity is so high that we can separate out charged particles coming from different directions. But we also had to develop new techniques, particle flow. We had to develop things to correct for neutral energies called fast jet corrections. Many things had to be developed, many new techniques, very powerful techniques using multivariate analysis, boosted decision trees, energy regression. And what was really remarkable for me as someone who's been in the field for many decades was this was all done in a few months. Once we got hit with this high luminosity, which we hadn't anticipated, the experiments had so much talent and so much energy in their legions of physicists that it was a matter of months before we had conquered this rather difficult situation. And we were able, by 2012, to enter really a precision era in which you see here, these are the cross-sections, production cross-sections for different processes, starting with W and Z production, then with jets, W plus photons, di-W, WZ, di-Z production. As we got more data, we were going to more and more precision. And you have to realize that this is over 5 orders of magnitude or so of different processes, but even this process is 6 orders of magnitude below the total cross-section. So we're always dealing with very rare things. This was partly, I should say, part of this, our ability to really understand these processes in ATLAS and CMS was the great help we got from the theoretical community. There was something of a next to revolution where they were able to calculate typically all the processes we needed at next to leading order and many to next to leading order, and some resummation at next to leading log. And we thank all the theorists who worked extremely hard to do that, because that gave us everything we needed. We had a good understanding of the detector, accurate predictions of the physics from theory, very precise measurements, excellent control of backgrounds, and putting this all together, it meant we were ready to hunt for the Higgs. So prior to July 4th, this was the situation. ElectroWeek, if you combined all the ElectroWeek data, and if you are new to particle physics or don't know particle physics well, all of the subatomic particles are somehow interconnected. So for instance, if you calculate the W mass, the W mass has actually a contribution from top and bottom via this kind of a process. It has some relationship also to the Higgs. And all the particles are somewhat interconnected, so at least within the framework of the standard model. So as we understand particle masses very well, their properties very well, we can make predictions about other particles. And the prediction was that the Higgs should be light if it's standard model. Then, in early 2012, the Tevatron made a measurement of, had already good measurements of the top mass, but made a really spectacular tour de force measurement of the top mass to an uncertainty of 15 MeV, which I never expected would be possible. And if you look now in this plane of the top mass versus the W mass versus the top mass, you see there are diagonals, and those diagonals correspond to where the Higgs would be with different masses. And what had happened in 2011 was that we had left very little space. This whole white region had not been white previously. We basically eliminated that, and we saw something of a little excess in the region that overlaps this green ellipse, which is where the W and top mass predict the standard model Higgs would be. So that was the big story of 2011. We had really eliminated a huge fraction of the mass range of where the Higgs could be. So moving on to the discovery, now very quickly, because I don't have a huge amount of time, the main production mechanisms are shown here in order of highest rate. So there's gluon fusion via a top quark loop producing a Higgs. You can have vector boson fusion where quarks from the incoming protons will radiate say W's, which can then fuse and form a Higgs, and then you have some quarks at high energy in the forward region. You have associated production of a vector boson, which is a W or a Z with a Higgs, and you can have associated production of TT bar with the top quarks with the Higgs. We try to use as many production modes as possible to get as much power as we can. We look for events, for instance, with forward jets, and that gives us some ability to have more sensitivity to this vector boson fusion channel, etc. Now, in terms of what are the most sensitive channels in the end to look for, especially in this range that had not been ruled out, sort of 120 to 130 GeV, these are the big 5 channels that we looked at in order of power, so to speak. But the main ones I will talk about here are the Higgs to 2 Zs decaying to 4 leptons and the Higgs to 2 photons, because these 2 channels produce very narrow peaks. So here I'm showing very old simulation data of Higgs to 2 photons. The 2 photons are here and here. You have a very steeply falling background from standard model processes, just photon radiation, production of diphotons, or even a photon and a fake photon, which has a falling probability as a function of the invariant mass of the 2 photons, which is not surprising. It becomes more difficult to produce these things at high energy. The Higgs signal would sit on this as a very small bump that would be distinguishable provided that your energy resolution, your mass resolution is extremely good. So both ATLAS and CMS spent literally hundreds of millions to have very, very good resolution of photons energies. Now, each experiment would have about 500 events in this mass range with a background of about 20,000 in the mass window. So the signal to background is not so great, but if you go into the more rare production processes, the signal to background increases. The other peak, as I mentioned, is Higgs to Z to 4 leptons. This is really nice. You can reconstruct the 2 Zs, then reconstruct the Higgs. You get a very nice peak with very small background, but it's extremely rare, so you have to wait a long time to get these events. And here, the difficulty is really getting down to very low momentum so that you collect all of these events with high efficiency. So this is what we presented on July 4th. This is the photon mass distribution and from CMS. And sure enough, we saw a little bump on a very steeply falling background. And if you're asking what's in this bump, it is a few hundred extra events with 2 photons that reconstruct to a mass of about 125 GeV. And if you ask how many collisions did this take actually to find, it was actually 10 to the 15th. So 1,000 trillion. And ATLAS saw exactly the same thing. Well, not exactly, but very close to the same thing at the same mass. And this is quite a strong coincidence. And then if we look also, this is, by the way, a nice event display of one of those events in the peak from CMS. Again, you see lots of debris from the other collisions, but these 2 red bars correspond to energy found in the electromagnetic crystal calorimeter corresponding to photons because there was no track pointing to them, so we know they're not electrons, for example. So in the Z's, you have what's shown in red here is what you'd expect in this ATLAS plot from standard model backgrounds. The green, this kind of off blue, and this blue here shows what you get if you had different Higgs masses. And there's not really anything here, there's not anything here, but there is something here. And in fact, that's exactly at the same mass as we saw the photons. And for CMS, again, you see a nice peak at 125 GeV. And here I show a nice Higgs to ZZ to four electron candidate from ATLAS. And the two red bars here correspond to electrons that produce one Z, and the two blue the other. And this corresponds to a mass of about 125 or 126 GeV. So this was a big event in our field. We made the announcement on July 4th of the discovery, simultaneously broadcast to Melbourne. These are the guys in Melbourne. You know, Aussies are pretty rowdy, so you can tell that they're... And what surprised me a lot was the press coverage. It really hit the press all over the world. I hadn't anticipated that at all. Some of the stories were kind of interesting, like 3 ways the Higgs boson discovery will impact financial services. This one I liked, how the Higgs could become annoying. It's thrilling, game-changing, but it could introduce some aggravating situations. And of course, we much prefer calling it the Higgs or the scalar boson. Just don't say God about it. Anyway, the question then was, we had something, and if you were paying attention at that time, there was a lot of comments about, we have a Higgs-like particle that's been found. We weren't calling it the Higgs. Actually, we were all calling it the Higgs inside the experiments, but we weren't really sure what it was yet. You know, it was very fresh. It certainly looked a lot like what we'd expect for the Higgs, but we didn't want to be irresponsible and jump to conclusions, so we called it Higgs-like. And so after the discovery, the question was, is it Higgs-like, or is it a Higgs we like? Is it really a Higgs or not? And so there are 2 main points we wanted to address early, 2 important fingerprints. Does it couple to other particles in proportion to their masses? That's one. If it's giving masses to the particles, that's exactly how it should couple, in proportion to their masses. And so there's slightly different proportionality factors for fermions and bosons, but there should still be this mass dependency. And does it have 0 spin and positive parity? And so we did studies with almost 3 times the data of the discovery, and I'll show you those momentarily. There are many other questions, mostly for current and future studies. If it's a Higgs boson, the question is, what kind is it? Is it elementary, for instance? Is it the first elementary scalar that's ever been found, or is it composite? Does it have any degree of negative parity? Does its couplings deviate from standard model expectations, which could indicate that there are other Higgs out there? There could be a more complex sector. There could be new physics, et cetera. So first I want to show you the masses. Masses are calculated mainly in the 2 channels I've described, the photons and the Z's. And you can see the 2 different channels from ATLAS average out to a value of 125.5, which is very close to the CMS average of 125.7. And the uncertainty is already very, very good. If you look at the couplings, I showed this CMS plot just because it gives you very clearly the dependency that you'd expect. The masses along here, the couplings, appear to be the couplings we extract under the assumption that it's a standard model Higgs, are proportional to the mass, once you take into account the proportionality factors being different. We looked at the spins in many, many different ways. We look at, for instance, angular information from the 2 photons, or all the angles from the 4 leptons, plus the different masses, et cetera. You can reconstruct all the kinematics and compare it to what you'd expect for 0 plus versus 2 plus, and you can see we were able to exclude in ATLAS the 2 plus at 99.9%. We've excluded many different spin 2 models. You can't exclude all of them with the data that we have. There are obviously a very large potential number of those. We've excluded spin 1, we've excluded 0 minus. So all indications are this thing is compatible with the Higgs. March last year, we went out with a little press release saying, we're calling this a Higgs. And so there was a news, hit the news again. I didn't expect that again. I'm really silly about that. I'm really naive about how much there was this news. It was a very was a very big news week that day. In fact, there was something else going on. I don't know if you remember, they were choosing the Pope. And then we saw this, which I thought was funny, the Higgs boson and the new Pope confirmed. But that was cited, that claim, the spin, the information that we'd shown was actually cited in the long report from the Nobel Committee as convincing them that it was time to give the Nobel Prize. And that went to Francois Englert and Peter Higgs. Robert Brout, who would have also certainly been on this list, unfortunately passed away in 2011. And we were very happy that they cited ATLAS and CMS and the discovery in this thing. Okay, we reacted calmly with dignity and sobriety. So let me just show you some recent results very quickly. I think I'm running out of time. I don't have a lot. I have 0. Okay, I've run out of time. We've seen now the Higgs in fermions. This shows CMS. We've seen excess in the taus at 125 GeV. We see excess in the BB bar pairs at 125 GeV. And in fact, we have a nice calibration from Z to BB bar, which is more than 6 sigma. And so we see about a 4 standard deviation fermion signal. ATLAS has a nice excess seen in the taus alone that's already 4 standard deviations. So we see the fermions. Most recently, we've looked at an interesting way to get at the width of the Higgs, which is otherwise, we thought, inaccessible. Turns out the on-peak cross-section is proportional to the couplings to particles in the ZZ decays and also the width, but the off-peak is not. I'm simplifying this a bit. And so if you take the ratio, it cancels. You have to take into account lots of interference. But we're actually able to set a bound at 4 times the standard model width, which is about 17 MeV. Okay, so the question is what comes next? I have to move very quickly. We're going to go to really rare processes. This is the total cross-section. Go down 13 orders of magnitude. We're going to look for Higgs to mu mu, and we think we'll find it in coming runs. We're going to improve the luminosity of the machine and go from a few dozens or hundreds of events to hundreds of thousands over the next few decades. And this will allow us to get the coupling measurements down and probe for new models of physics. But even more precision and higher energy is required. I'm just 1 minute away. And the next speaker, I think, will address this. We need to understand the implications of this Higgs boson. Is the universe completely fine-tuned? Is there something that balances it out like supersymmetry? And there are many things being planned in the collider arena as well as the non-collider arena. But there's the possibility of a linear collider in Japan, which would be an E+ machine with very high precision. There's the possibility of building a new, this is the LHC, which I showed you was quite big. CERN is considering a much bigger VLHC, or even bigger one. And that would have an E+ E- version that would look very carefully at the Higgs. There's the possibility of a linear collider near CERN. And this would have obviously very nice capabilities. This CLIC would have a capability of scaling to very high energy if necessary. And finally, the Chinese, who have built some big things in the past, like the Great Wall, are considering the Great Ring of China, which would be another massive machine. So to finalize, that would have also an E+ E- version to study the Higgs. So in summary, a new boson has been found. It took now 50 years since the idea was hatched, 20 years to design and build the experiments, 3 years to acquire the data, a generation of work by thousands, and all I got was this T-shirt. But actually, of course, it was a giant leap for science and a breakthrough of the year. So, thank you. There's time for 3 questions, in case you didn't hear that. And I don't know where the microphones are. Any questions? Oh, there's one here. Yes. You.
So when you look at the Z channel, one of the Z bosons is off shell.
That's right.
How do you know it's a Z boson?
He said, when we look at the ZZ channel, one of the Z's is off shell. How do we know it's a Z boson? as opposed to just continuum. We know pretty well, again, we have very good calculations of the continuum background, the ZZ background. So we're looking for an excess. The other thing that makes us fairly confident that these are not just continuum backgrounds and this is a real Z that's part of the, well, it's an off-shell Z that's part of a Higgs decay, is that we do see this very narrow peak in these samples. So we know it's coming from a resonance. The assumption that the Higgs is, I mean, all of this kind of ties together that way. But in any given event, one by one, you can't say anything. This is all done statistically. There's one there. Huh? So the question was, is there any plan to combine ATLAS and CMS to really improve these results? And no, we get along so badly, we don't talk. Actually, no, we get along very well. And the plan is to combine. But what we want to do is we want to combine on the final, what we call legacy results from run 1. So I know that CMS is working hard to get those out. You'll see some papers coming out in the next few months. ATLAS is doing that as well. As soon as the published results, the final results, because everything you've seen here, for instance, is at some level preliminary. Much of it's preliminary. Once we get the very final results, we'll make a final combination, because we don't want to do this. We don't want to give too precise conclusions that may differ. So we're waiting until we get all the final results. So I think sometime in 2014 or sometime this year or early next.
I think we have to move on. Thank you very much.